time to look at another GCSE exam paper. Now this is, let's scroll across and find it. This is, okay, I'm quite far away from it. Combined Science Foundation paper of 2022. Okay, let's go. Now the first question says some information about Group 1 elements. It says, using the periodic table, can you give the symbol of another element? Now there are obviously several options below potassium there. I'm going to go with, I'm right in the right place, I'm going to go with rubidium. Okay, either cesium or francium would be fine. It then says give the atomic number of lithium. Now this is the smaller of the two numbers on the periodic table, which would be 3. Now it says there, describe the trend of melting points of elements of the elements in figure 1. Now it's 2 marks. You're going to need to say 2 things. So as you go down the group here, what happens to the melting point? So as you go down the group for 1 mark, the melting point decreases. Okay, so that's what you got to say. As you go down the group, the melting point decreases. Brilliant. So 2 marks, 1 for each point there. Now the next one says the elements in group 1 react very vigorously with water. Students suggest the method to see what happens when sodium reacts with water. Okay, so put some safety glasses, takes a big chunk of sodium and puts them in the container with a few drops. Now, it says, give the name of the container shown in figure 2. Easy peasy. That is a test tube, isn't it? Okay, that's a test tube, quite obviously. Now, if you'd written boiling tube, because obviously it doesn't give you any indication of size there, that would be absolutely fine. The teacher says that method is not safe. It's not safe, okay? Why? Why is step 2 unsafe? What would you change? That is a pretty big chunk of sodium. That's more sodium than I would put in when I was trying to make it exploding on the ceiling, okay? So basically you need a smaller piece of sodium. Okay, that gives you a lesser reaction. It'll basically make the reaction slower, which is good. Now, step 3, what are you going to do there? A few drops of water. Ooh, well, obviously, you're going to use a large trough. You are. More water, which means more heat is absorbed. Okay, nice. Okay, so that's the first row of pages done. Let's move on now to the second row of pages. Oh, question 2. Here we go. It says some reactions are exothermic and some are endothermic. What does an exothermic reaction always give out? Okay, now the answer is heat. Now I realise a lot of exothermic reactions will also give out light, but they don't all give out light. So therefore, stop thinking of a fire, it's just heat. Now, which of those pieces of equipment in that picture would you use to measure the temperature? Well, A is quite obviously a thermometer. Okay, D would be the solution, B is the beaker the cup's being held up in, and C is the cup. So therefore, it's got to be A. Now, what is B called? Well, it's a beaker. Okay, we put it in a beaker so it doesn't fall over. Otherwise, you'll make a mess. Okay, now, it's made from polystyrene. Why is polystyrene good? Because it's a good insulator. If you're trying to measure the heat change in here, you want to try and keep the heat in, so you're not measuring heat loss. Right, I'm a bit zoomed in here. I'm going to zoom out a little bit. Now, the next one says, the results are given there. Calculate the change in temperature. Okay, so to calculate the change in temperature, we basically need to see what happened to it as time went on. So we're going to say at the end it was 16.1 minus at the beginning it was 18.6 equals that's terrible, equals minus 2.5. Okay, so gives a sign and a unit. Well, I mean, it tells you the unit up there is degrees C, so just make sure you write that in or you'll lose one of the 3 marks. 1 mark for the number, 1 mark for the sign, 1 mark for the unit. Job done. Now, the solid in experiment contained only NH4 plus and NO3 minus ions. Give the formula and the name of the solid. Well, that's a 1 plus, that's a 1 minus, so therefore the formula will just be NH4NO3, and that is called, as you may or may not know, I'll write it down here, ammonium, not pneumonia, ammonium nitrate. Because the NH4 plus is the ammonium ion. Fantastic. Right, moving swiftly on to question 3. Let's have a look. Oh look, it's a molecule obtained from crude oil. Brilliant. Give the names of 2 elements in that molecule. Look, it's a hydrocarbon. That means it's carbon and hydrogen. Lovely, 1 mark for each. Now, what is the molecule? Is it an oxide? No, an oxide would have oxygen in it. Is it a fullerene? No, that's a big tube or ball. Is it a ring? Is there a circle going on there? There isn't. It's a chain molecule. Now, what is the relative formula mass of that compound in figure 5? Okay, so all you've got to do there, remember, is there are 3 C's times 12, that equals 36. There are 8 H's, there 1, that's 8, and that means it's 44. Okay, lovely. Right. Crude oil can be separated in many fractions. This is a very common kind of question. Okay, they're just asking what a fraction and what use of that fraction is, and some of these are easier than others. Now, can I just say, when you do this, please don't do, okay, this one is obviously fuel for cars, right? Can you not do, when you do this, sort of like, I'm going to draw one in a line like, whee. Can you not do that? Can you just do a straight line? It makes my life easier. And I'm even going to undo that because it just annoys me. Unless you want to annoy me, in which case do a complicated pattern. But if I can't tell which box it's going to, I'm not going to mark it right, okay? So do a squiggly line at your own risk. That is fine. It doesn't have to be straight. Just make sure it's clear where they go. So kerosene is for aircraft, bitumen is used for making roads, and petrol is for cars, okay? Make sure you do a nice straight line. Again, make it easy to mark, okay? For your real one, obviously. If you want to annoy me and do squiggly lines, absolutely fine. But for your real one, make it easy for your examiner to mark, okay? Now it says, hydrogen chloride gas and sulfur dioxide gas dissolved in separate test tubes of water. Blue litmus paper is dipped in each test tube. What would you see? Okay, well, hydrogen chloride gas, HCl, aqueous, because it's dissolved in water now, that would go red because it's an acid. Okay, SO2 gas, aqueous, would also go red because it's an acid. Okay, remember, sulfur dioxide dissolves in water to make an acidic solution, acid rain. Brilliant, well done guys, so far so good. Let's have a look at this last one. This is about the halogens in group 7, which is a green gas at room temperature. Okay, now you've never seen or heard of fluorine before. We don't have that. It's ridiculously reactive. We're not allowed it. Bromine, you may or may not remember from looking at these in a test tube, is a red liquid. Iodine's a purple solid, so it's chlorine is the green gas. They all react with heated iron wool. Okay, there's speeds. When iron wool is heated with chlorine, iron chloride is formed. Write a word equation. So it tells you everything you need there, apart from, okay, the iron wool is just iron. So it's iron plus chlorine makes iron chloride. The only thing that doesn't tell you is it says iron wool. Now you get 1 mark for iron and chlorine, and 1 mark for iron chloride. Okay, now it says give the name of the halogen in figure 6 that's most reactive. Well, which one, you know, which one do you think, which one reacts the most quickly? It's the chlorine. If it reacts quickly, it's the most reactive. Sorted. Right, we are flying through this, guys. Let's keep going. So next it says 34.4% of the mass of iron chloride is iron. So they're giving you the percentage. Calculate the mass of iron and the mass of chlorine in 125 grams of iron chloride. Okay, so for this, all you do, right, is you just say 34.4 divided by 100 times 125. Okay, now that basically takes it away as a percent. That stops it being a percentage. Okay, and then that tells you how much there is in 125. So that tells you how much there is in 1. That tells you how much there is 125. Okay, so that gives you mass of iron is 43. That will work it out. Now, so you've got 125, 43 of it is iron. So 125 minus 43 gives you, according to my calculator, 82 grams of chlorine. So 1 mark of each. It says, alkenes react with halogens. When iron chloride is added to the reaction mixture, it's much faster, but the products are the same. Use the words. The iron chloride speeds up the reaction because it is a catalyst. That's something that speeds up reaction, isn't it? After the reaction, the mass of iron chloride is unchanged. Remember, a catalyst speeds up reaction without being used up by giving a lower alternate reaction pathway with the lower activation energy. That's what we're looking for there. Now, number 5. Oh, I remember this is on the higher paper. This is good. Name a piece of art. Look at the picture. Here is our thing. We've got a measuring cylinder with some graduations. Now, we used a gas syringe for this because, you know, we've got gas syringes. So what would be better to measure the volume of gas? Well, it'd be a gas syringe. You know, I wasn't just flexing when we got those out. You know, look at the money we've got at Dean Magna. They are actually better, okay, because it has a higher resolution. More markings. Right, calculate the mean rate of hydrogen over the first 90 seconds in centimeters cubed per second. Right, so first thing you've got to do is you've got to realize, of course, that 90 seconds is a minute and a half. So you find 90 seconds on here, that's 1 minute, okay, so around about here. You then read up and see here, do it with the ruler, it's 29. Now obviously, you are allowed a bit of leeway there. If you'd written 28 to 30, you'd be fine, okay? But the mass is actually 29, right? Now, you very simply divide that by 90, and that will tell you in centimeters cubed per second, okay? Which is actually 0.32222, okay? Again, error carried forward allowed. If you put 28 divided by 90 and wrote what your calculator said, you would have got all the marks, okay? Now, 3, a student measured the volume of gas for 10 minutes. They did. State why they could have stopped at 9 minutes. Well, let's have a look. Here's 9 minutes, here's 10 minutes. The line is horizontal. What does that mean, okay? The volumes were constant. Volumes were constant. That means, obviously, as we know, the reaction has stopped. Right, the experiment was repeated, but with an acid of a high... Oh, hang on, I'm moving the page. Oh, that's annoying. Oh, I'm going to mess the paper up now, but never mind. The experiment was repeated with an acid of a higher concentration. The rate of reaction was faster. Explain why the rate of reaction increases when the concentration of acid is increased. 2 marks, so 2 points, right? So, if you have a higher concentration, essentially you've got more acid particles. Okay, that means more frequent collisions. More frequent collisions. A higher frequency of collision, more collisions per second, something along those lines, okay? Nice. So, a student suggests 4 other ways of increasing the rate of reaction, which is correct. Okay, so if we use the same acid but at a lower temperature, is that going to increase the rate of reaction? No, it's not. Use a large trough. What difference would that make? Use a smaller flask. Again, what difference would that make? Use the same metal but in a powdered form. Okay, if you break it up, is it going to react faster? Yes, it is. The answer is D. C very kindly asks you, it says the apparatus in figure 7 can be used to measure the rate of reaction between marble chips and hydrochloric acid. The student needs different sized marble chips. How can the student make smaller marble chips from large chips? Okay, well, what you got to do, 2 marks. Okay, so we're going to say you're going to have to break the large chips. Now remember, marble is stone, so don't say cut, say break or crush. It's a stone, okay? Now, where are you going to do that? You're going to do it in a pestle and mortar. That's where you're going to do that. You're going to do it in a pestle and mortar. Okay, rolling through quite nicely now. Let's get on to what is probably the last section of pages. Question 6. This question is about gases. When sodium is added to water, gas is produced. Which observation shows that a gas has been produced? Now, you may have heard me use the word effervescence, which means bubbles. So, bubbles are produced, essentially. Effervescence is seen. Some damp litmus paper is placed in the gas. The litmus paper is bleached. Which gas bleaches damp litmus paper? Now, you need to be aware of the 4 gas tests here. You need to know how you test for these 4 gases. Now, carbon dioxide, is lime water turns cloudy. Not that one. Chlorine bleaches damp litmus paper. It's that one. Hydrogen, okay, lit splint gives squeaky pop. Oxygen, glowing splint relights. There we are. Now, question C, it says, when calcium carbonate is heated, it decomposes, process called thermal decomposition. When 5 grams of that is heated, the mass of the solid is 2.8 grams. Calculate the mass of carbon dioxide that's been released to 3 significant figures. Now, you know by the law of conservation of mass, that if there's 5 grams here, let's just write 5g, there's going to be 5 grams over here. Okay, so all of that is going to equal 5 grams. Okay, now, if you know that 2.8 is this, you can work out what's left, okay, by doing 5 minus 2.8. Okay, so that obviously gives you, I'm going to write here 2.2, but equals, that's an equals, not 5. But obviously you've got to do it to 3 significant figures. That is only 2 significant figures. Now it's 3 significant figures. That's a 0, obviously not a heart. Great, okay, so let's now look at D. It says, that's an atom of helium. Wow. Why is helium inert? Now, I keep saying the word inert, and nobody ever listens to me, and then you all say, when this kind of question comes up, what on earth does inert mean? You've never told us that. Well, when we discuss noble gases, I always say they are completely and utterly unreactive. Not a little bit unreactive, completely unreactive. And that means they are inert. That means completely unreactive. So, why is it inert? It's got a full outer shell, basically. You just got to say 2 electrons, hang on, electrons, my pen's having a funny 5 minutes here, in outer shell for 1 mark. So what does that mean? Why does that mean it's inert? Okay, so it doesn't gain or lose electrons. That's it. Now, helium is used to fill balloons. State one property of helium, apart from being inert, that makes it suitable for filling balloons. Well, you need to use the key term here now. It is less, and what am I doing? I've done something. It's less dense than air. Air, okay, so it's less dense than air. Make sure you use those terms, okay? If you say less dense than oxygen, it doesn't matter, okay? You've got to say it's less dense than air. Now don't say it's lighter, say it's less dense. Right, here comes the biggie. So gases in the early atmosphere. Let's have a little look-see here. Natural processes and human activities have altered the relative amounts of these gases in the atmosphere. Explain how the relative amount of these gases has increased or decreased over time. Okay, so we have got to say what has happened to these gases. Okay, now what you need to do here is you need to show an explanation that is clear and logical. Okay, now let's just go through these one at a time, right? So H2O, water vapor. Okay, that was given out by volcanoes. Okay, now obviously lots of volcanoes erupting, Earth's very hot. Okay, the Earth then cooled, because obviously it cooled down, and the water vapor condensed to form oceans. Okay, that's what happens to the water vapor. Okay, it's given up by volcanoes. The Earth cooled to the point where the water vapor could then condense to form the oceans. Great. Now I'm going to jump. To here because it's a bit easier, right? So CO2. Okay. Now some things happened to lower the amount of CO2. Okay. Now, obviously, some dissolved in oceans. It did. Some dissolved in oceans and basically made animal shells. They took that and made carbonates with it, animal shells. Okay. Now, the rest was photosynthesis. Okay, photosynthesis. Now, so carbon dioxide was taken in. Photosynthesis was done by plants. Now, this obviously released oxygen. Obviously, which is the third box. Okay, it released oxygen. So I'm almost done going through this past paper now. Hopefully the person who's annoyingly knocking on the door will go away while I'm going through a past paper and making a video. There we go. Okay, so the plants released oxygen. Now, what we've then got to say, we've just got to talk a little bit about human effects. Okay, so by burning fossil fuels, we are increasing CO2 in atmosphere. Okay, and finally, by deforestation, that means less CO2 absorbed. CO2 absorbed by trees. Okay, by trees. Nice. Okay, there we are. Paper done. Well done, everyone. See you soon.